Hello, Allie. I'm Bailey. This is Friday, and I'm at the bus stop for a few minutes, so I'll get you started on your class and hope this video is working for you. And it's Friday the first month, the 9th day, and the year 2015. All right, I'm going to be looking at a topic which will not knock your socks off because it's sort of a rehash. But I guess we saw these concepts when we looked at indefinite integrals. And now that we're looking at definite ones, we just need to apply it to this situation. So let me do this. I'm going to investigate this concept by looking at the function y equals cosine x. And I'm going to be interested in it over this interval, 0 to 3 pi over 2. So you'll be taking these notes and draw the graph. Cosine curve starts at 1, and here's our 4 tick marks. We have pi over 2, pi, 3 pi over 2, 2 pi, and we're interested in it between here, 0, and 3 pi over 2. It starts at the high point, which for the cosine curve is 1. It zeroes out at pi over 2. It gets to the lowest point, which is -1 at pi, and then it comes back up at 3 pi over 2. Then it will finish by going back up to 2 pi. The area we're interested in, and I want to draw this a little better. Come down a little steeper, so it's more of a smooth curve. I have sides that look kind of straight when there really aren't any straight sides to this graph, so hopefully yours looks better than mine, but that'll do. So we're interested in the area this time, bounded by this curve and the x-axis on this interval. So here's one part of it, and here's the other part of it. All right. Let's look at the tool that will get us this area, and that's our old friend, the integral, who has taken on a new look with these numbers. So I'm going to look initially at the area in this first part. So that would be from 0 to pi over 2, and the curve is the cosine curve. And I want to calculate that with respect to x. And we learned yesterday how to do that. So I'm going to have you do some of those today with trig functions in them. Some definite integrals with trig functions in them. Let me move this. So this one turns out the integral of cosine is the sine. And you can always check that by taking the derivative of this. Does it get you back to that? It does. And then we learned about this new notation where we're going to evaluate this sine x first at pi over 2 and then subtract sine of 0. So let's do that. Keep running out of room. So this is experimental here. All right, equals sine of pi over 2 minus sine of 0. And sine of pi over 2, let's see if I can think of my unit circle. Pi over 2 is up here, so the coordinate there, little monkey math, 0 right and left, 1 up. Second coordinate is our sine, so this value is a 1. And sine of 0, this is 0, I'm sorry, it's 1, 0. My monkeys aren't with it today. 1, 0. So we have the second coordinate is sine of 0, 0. So we get 1 minus 0, or 1. So this, going back to the picture here, what if I can just zoom back? Always the opposite. Now it's not too easy to see. I didn't feel like setting up my board tonight. So you get the little paper version. All right, so we went the area under the cosine curve from 0 to pi over 2, and that value is sorry, the floating graph here. I don't know why it's not holding where I want it. Okay, I guess that'll do. This is a 1 under here we've just established. So let's go ahead now and see what happens when we crank out the integral from pi over 2 to 3 pi over 2. So I'm going to do the same sort of thing, except I'm going to use the integral from pi over 2 to 3 pi over 2. And again, it's the cosine curve. We already discussed what the integral is, and that is the sine. And we just put in these new limits of integration. So I'm going to do the sine of 3 pi over 2 minus the sine of pi over 2. The sine of 3 pi over 2, looking at the unit circle real briefly, 3 pi over 2 is down here, so that is 0 minus 1, second coordinate minus 1, minus, we talked about sine of pi over 2, and that was 1, and we get a minus 2. So, does that surprise you that the integral for this value right here turned out to be negative? I don't think it should. So that area under there is minus 2, because we had talked about that in many different ways in different graphs, different problems when we had indefinite integrals, even that one on your test where you had to mess with that idea. So it's the same when we're looking at definite integrals. If I ask you to find the area, and you must identify whether the graph is above or below the x-axis, and this is below, so you would have to calculate this part and take the opposite sign in order to get the area to be positive. So let's see what happens if we discuss the integral from 0 to 3 pi over 2. And if we understand this, we wouldn't really have to do this, but we're kind of just proving that our ideas are sound. So what if I'm going from 0 to 3 pi over 2? So once again, when we're looking at this graph, 0 to 3 pi over 2, are you expecting a positive 1 and a negative 2? Are you expecting the integral to crank out a negative 1? Let's see if our expectations are true. So the integral of cosine, again, is sine. This time, we're evaluating from 0 to 3 pi over 2. So it equals the sine of 3 pi over 2 minus the sine of 0. We already talked about the sine of 3 pi over 2. It's minus 1. And the sine of 0. And we did get the minus 1 as we expected. So what is happening here? I'd like you to take a note about it in your comp book in words. The definite integral is just a machine. It doesn't know if the graph is above or below the x-axis, and it will always be calculating the areas above as positive and the areas below as negative. So let us make a note about that. The definite integral will take the area above the x-axis as positive and will compute the area below the x-axis as negative. All right, so you already knew that, I hope, but I'm just going to emphasize it. And the definite integral will take the area above the x-axis as positive and will compute the area below the x-axis as negative. So, what would we expect then, having reviewed that concept, if we went from 0 to 2 pi all the way, and the curve is the cosine x dx? So, what would happen if we're doing that? Well, let's look back at our graph up here. I can get it back in view. My camera challenged self. All right, so here we're going from 0 to pi over 2 this time. What do you expect will happen? Make your prediction and write it down, and now we'll actually do it down here. So the integral from 0 to 2 pi of cosine of x equals sine of x from 0 to 2 pi, which will give us sine of 2 pi minus sine of 0. Sine of 2 pi is the same as sine of 0. They're the same spot on the unit circle. They're both 0. So was your prediction 0? It should have been, because the area above here is 1, this will also be 1, and the area below will be calculated by the integral as negative 2. 1 plus 1 minus 2 gives us 0. If I wanted to calculate the area of such a thing, I will have to set it up piece by piece. I'd have to do the integral from 0 to pi over 2, which is positive, of cosine x. And then I'd have to do the next section and put a minus sign in front of it, because that's where it went below the curve, from pi over 2 to 3 pi over 2. And then I would have to do the last section where it went above the curve again, from pi over 2 to 2 pi cosine x dx. All right. So we'll be looking at problems that will, and I'm not going to compute all that. You've seen enough to see that it's going to come out, this is going to come out to 1, this is going to come out to a negative 2, but the negative here will cause it to be a positive 2, and this is going to come out to a 1. So adding those up, I'm going to get a area under the curve to be 4. All right, that's really about all I have to say today, and as I said, it wasn't going to be a new knock your socks off revelation, but I wanted to emphasize that. And the one I really want you to work on that will exercise this is in your book. So one of you needs to get your book, and it is 4.4, number 66. And I just want you to do parts A through E, because that will show me whether you understand this concept. So if you would do that one, and then just some more practice with definite integrals until I come back in a few minutes, is number 4.4, and you have this on your handout. From yesterday, 27 to 35 odd, 36 through 38, and number 40. So that's your assignment for today and for this weekend, so be working on that. But I'd like you to start with this one, as it emphasizes what I just talked about. So one of you get your book so you can see that one, and you have the rest on your handout. All right. Hold down the fort until I get there. Bye.